Well, to find relative extrema, that's a different story. And we talked about what they are, and I think you got the definition clearly. And really, this picture that I had up here makes, relative maximums and minimums fairly clear what they mean and how the definition works. I hope I talked my way through that all right. But to find them, so how do you find relative extrema? So to find them, investigate the set of points where the gradient of f is 0 or undefined. So these points are called critical points. So what is a critical point? Critical point, let f be defined on an open region R containing the point x sub 0, y sub 0, then the point x sub 0, y sub 0 is a critical point if one of the following is true. Either both partials are 0, that means the gradient would be 0, or the partial of x, partial with respect to x, or the partial with respect to y doesn't exist. So the first condition, of course, implies that the gradient vector is the 0 vector. So then every directional derivative must be 0. Remember how you calculate a directional derivative. You dot this with some other vector, that gives you the direction, of course, with the 0 here and here. So every directional derivative is 0. I don't know if you understand what that is saying, but what that is saying is, since every directional derivative is 0, then if you try to go in any direction at this point, it's flat. Okay, so hence there must be a horizontal tangent plane. That's the secret. There must be a horizontal tangent plane at the point x sub 0, y sub 0. So that makes it at least a candidate for a relative extremum, but it need not necessarily be a relative extremum, and we'll see why later. So we know this. We know what a critical point is now, place where the gradient is 0, or a place where both partial derivatives or either partial derivative does not exist. So relative extrema, according to our theorem here, only occur at critical points. So if x has a relative extremum at this point on an open region R, then that is a critical point. So back to example 1. Okay, f of xy is sine of x plus sine of y plus sine of x plus sine of y, doesn't matter. The partial with respect to x is cosine of x. The partial with respect to y is cosine of y. And both of these are 0 at the point where x is pi over 2 and y is pi over 2. So within any open disk R centered there with a small enough radius, you can see that f is smaller than f of pi over 2, which happens to be sine of pi over 2 plus sine of pi over 2 happens to be 2. So therefore pi over 2 is a relative maximum. And let me see if we can go back to our picture and see that. Pi over 2, I guess, is approximately 1.57, let's call it. And I think what this is trying to show right here, this is x is 1.57 here, and y is 1.57 here. So it's trying to show that there is a peak value of 2. And I don't know if you can see the 2 here, but the 2 would be, I don't have a marker for the 2, but it would be right that top value. And that 2 is a maximum. And so that's what our examples show here. Okay. Find any relative extrema and identify as min or max if possible. For this example, g of xy is x minus 3 squared plus y plus 2 squared. And of course that means g, the derivative of g with respect to x is 2 times x minus 3. The derivative with respect to y of g is 2 times y plus 2 times the derivative of the inside function. In both cases was 1. And so both of these are 0 at the point where x is 3 and y is negative 2. Any other value of x or y will make g positive. See, because if you square this and square this, well, you're going to get a positive number. So, 3, negative 2, 0 is a relative minimum. So I'm going to draw you this picture, and I'm going to show you. I'm also going to draw the xy plane in here. I'm going to say h of xy equals 0, so I'll get the xy plane in my picture. So you should see this is, by the way, a paraboloid. Its cross section should be circles. And here is the picture of that paraboloid. By the way, it's centered at the point where x is 3 and y is negative 2, so I should be able to show you that. Where x is 1, 2, 3, that's here, and y is negative 2, that's here, should be a minimum point. And I think you can see that. Maybe from the side would be easier. But maybe even from the bottom, right there is the minimum point. Notice y is negative 2 and x is 3 at that minimum point.